Okay, let's go over some questions from Unit 1 Module 2 homework, and these are the questions that came up during my office hours. Yeah, let's try this question. Okay, um, okay, we're dealing with a gas. Okay, the initial image below is a static view of a tiny section of air inside a balloon at 300 Kelvin and 1 atm pressure. Which of the other images best represents the same section of the air inside the same balloon at 600 K and 1 atm pressure? Now we're dealing with the gases. When we deal with the gases, we use the ideal gas relationship, which is PV is equal to number of particles times Boltzmann constant times the temperature. Now what we are told here is we have the same pressure and same volume, because you can see that we are looking at the same cross section, meaning we are looking at the same volume, and then Kb is a constant. So what we are dealing here is two parameters on the same side of the ideal gas stove over here, right? So when you have a situation like this, what we have here is N times T being equal to a constant. Okay, in other words, now N is equal to a constant times 1 over T. So in other words, our N is inversely proportional to the temperature. Okay, so what is that? Now let's see what we have. In the initial case, we have 300 Kelvin and we have doubled the temperature. So if we are doubling the temperature, the number of particles must decrease by the same factor. That means the number of particles must be halved compared to the original or the initial condition. So we have 4 in the initial state. Okay, after increasing the temperature to 600, you should have half of that, which is 2. So the correct answer must be option B. Now, for the people who are mathematically oriented, we can do it this way as well. So we have the initial state, let's say N1 particles, and that is going to be one that's going to be inversely proportional to the initial temperature, which is T1, and then we have N2, and that's the second state. Okay, after increasing the temperature in this case, and that should be inversely proportional to the second temperature, which is T2. And here's my 1, here's my 2. If you divide 2 by 1, you should get N2 over N1, and that is equal to T2 over T1. No, it's the other way around. Give me a second. That should be equal to T1 over T2. Okay, because what we're dividing here is 1 over T2 by 1 over T1. So if you do that, you're going to get T1 over T2. Okay, anyway, now this is the relationship. Now if we just plug and chug now, we're looking for N2. That's what we do not know. Okay, N2 is what we're looking for, and then we have the N1 to be 4, and the T1 happens to be 300 Kelvin, and then T2 happens to be 600 Kelvin. So this is 1 over 2, and therefore N2 must be equal to 4 times 1 over 2, which is 2. That's how we got 2. That's how we got 2, option B as our answer. Let's do another one, and I want us to remember this relationship. Oh, actually, you know what? Maybe this relationship. Okay, when we do another problem like this, let's go to versions. Let's go to version 8 for a second. Okay. All right. Here's the thing again. So again, we have everything the same. Volume is the same. Pressure, volume, N, K, T. Pressure is the same. Volume is the same. And then we are just changing the temperature. Okay, we are dealing with N and T, and what we realized was N is inversely proportional to temperature, right? And then with that, we derive that N2 over N1 must be equal to T2, I'm sorry, I always mess that up. T1 over T2. Okay, that's the relationship we came up with. Now let's plug and chug. We're looking to solve for N2, and N1 is 4. Here's 4 particles, and that should be equal to T1, which is 300 Kelvin, divided by T2, which is 150 Kelvin. So this should be equal to 2. Now 4 into 2 must be equal to 4 times 2, which is 8. So that should be our option C. Okay, that's that. Let's do one last question. Version C. All right, this time we are dealing with, we're changing both the temperature and pressure, which is cool. All right, anyway, now again, we're still dealing with the same ideal gas law. PV is equal to N times KBT. We still have the same volume. This is good. And then, but NT and P are the wild cards. I mean, they can change. Okay. So what we have here is, let's see. So, okay, pressure divided by N divided by T is equal to a constant. That's what we have. Okay. Now let's do the same thing. So we have P1. So that means we have the initial conditions. We have the pressure 1 divided by the number of particles 1, and then T1, and that must be equal to P2 divided by N2 and T2. Okay. Now what we want to do is we can plug and chug here. Okay, so when it comes to pressure, this is my initial pressure, here's my final pressure. So you know what, let's plug and chug them because it's easier that way. Now if you want to do it this qualitatively, we can do that as well. So we are doubling the temperature. Okay, that means the number of particles should decrease by a factor of 2. That will bring it down to 2. Okay, and then we are decreasing, we are halving the pressure. Okay, if we do that, the number of particles should decrease by a factor of 2. Again, should be 1. Okay, so I'm pointing at D now. Let's see if we are getting that with our mathematical approach as well. So we have P1, which is, we'll plug and chug now. P1 is 1 atm divided by N1, which is 4. Here's 4. And then we have the T1, which is 300 Kelvin. This should be equal to 0.5 atm, which is P2, divided by N2 is what we're looking for. And then the temperature is 600 K. Okay. And now I want to find N2. Therefore, I'm gonna take that to my left-hand side. N2 must be equal to 0.5 divided by 600, because units cancel out nicely. 600 multiplied by 300 times 4 divided by 1 atm. That's what we have. And then so what do we get here? So we have 300 canceling out. We're gonna have 2 here. We're gonna have 2 here. And then this is 0.5. 0.5 times 2 is 1. So N2 is gonna be equal to 1. So you're gonna have only 1 particle of gas in there. That's how we get 1 mathematically as well. So yeah, here's basically what we're doing here is we are just practicing using or applying the ideal gas law. That is it. Okay, I think that should be enough now. Right, everybody. All right, so let's broadcasting. Okay, anyway, let's go over another question that came up during one of his hours. Well, this question over here: predict what would happen to the particle density. So, yeah, particle density. We're talking about ideal gas here. Particle density of air if both pressure and temperature were double from their initial values. Okay. Now here's the thing. Again, we're going to assume the ideal gas behavior. Okay. So if you assume the ideal gas behavior, we're talking about, let me have a different color actually. We're going to have blue. Okay. We know the pressure times volume is equal to number of particles times kb over T. And then if you want the density, I'm going to have the volume moved to the other side. I'm going to have V divided by N is equal to, no, the other way around, N divided by V. N divided by V, which is the particle density as defined in the question, is equal to the pressure divided by temperature. And then you have the 1 over kb constant. Right. So what this tells us is this is N over V is the density we're talking about. Let's call it rho for, I mean, just to use a term for that. Okay, the particle density is directly proportional to the pressure and then inversely proportional to the temperature. That's what it means. Okay, so just to make sure we are on the same page, this rho here is the particle density. Particle density, that means amount of particles per unit volume. Okay, so in other words, this is rho. Okay, now we have this relationship. The question is asking what is going to happen if both the pressure and the temperature were doubled from their initial values. And then here's the thing. Okay, here's what we had in the beginning, this 1. Okay, and then in the second one, let's say this is rho 1, rho 2, and this should be 2 times the initial pressure. We have double in the pressure, and then 2 times the initial temperature. We're doubling the temperature. Right, here's the thing, that this 2 cancels out, and then we're going to end up with the pressure over temperature as before. Okay, and we see that 1 is equal to 2. That means the particle density, initial particle density, should be equal to the final particle density. So there's no change in the particle density. Density would not change. So that should be this answer over here. Okay, let's look at a different version now, maybe. Version B. Let's try this as well. Predict what would happen to the particle density, number of particles in a unit volume. Okay, anyway, if the pressure was doubled and the temperature was reduced to half from their initial value. Okay, again, we did have this relationship, the particle density, or N over V is equal to pressure divided by temperature. So this is coming from, we just rearranged our ideal gas law. That's what we did there. Okay, or in other words, we can say the give me a second, we came up with a term for the particle density. Is the particle density is equal to rho, and then what this says is the particle density is directly proportional to pressure and inversely proportional to the temperature. Okay, now let's see. So this is what we have initially. So we have O1, we have pressure and temperature. What we're going to do is we are going to double the pressure. It means it should be 2 times P now. And then we are going to decrease the temperature to the half of the initial value. That means we have T divided by 2. Okay, so this means what we have here is 2 times 4, 4 times P over T. Okay, so you know the P over T is our initial value. So I mean, we can do another thing actually. So we can do like this is our first equation, this is our second equation. If you divide the second equation by the first equation, you're going to get rho 2 divided by rho 1 is equal to, okay, 4 divided by 1, right? So what we have is, let me write it down, 4 P over T divided by P over T. You can see that this cancels out. You're going to get 4 over 1. So that means rho 2 is equal to 4 times rho 1. Or the particle density has quadrupled. Yeah, we have an option like that. Density would quadruple. Okay, so that should be the answer for version B then. And then let's go to version C. Let's take another stab at it. Okay, so again, we have the particle density. I'm not going to derive it again. So particle density is directly proportional to the pressure and inversely proportional to the temperature. That's what we need. This is our initial value. And then our final particle density is proportional to pressure, which was reduced to half of the value. So we have pressure divided by 2, half, and the temperature was doubled from the initial value. So you have 2 times the temperature now. Okay, so if you rearrange this, what we have here is we have P over T, okay, just like before, but in the denominator we have 4. Okay, so that means this is 1, this is 2. If you divide 2 by 1, you're going to get rho 2 over rho 1, and that is going to be 1 over 4 now. I mean, you know, just to make sure everybody's on the same page, here's 1 over 4 P divided by T divided by, this is the rho 2, and then we have in the denominator P divided by T, because that's the initial pressure and temperature. So P over T cancels out, and we're going to get 1 over 4, meaning our second density, or the final density, is 1/4 of the initial density. The density would not change, it would double, so it would be half, the density would reduce by 1/4 of the initial value. So it should be option E. Okay, so that is that. All right, so I want to go over a couple of questions from Unit 1, Module 2 homework assignment. And if I go here, I'm referring to this question over here. Let's say there are different versions. I did not know which version you're going to get, but let's consider this one, okay? Now, we have an ideal gas in a tiny container, okay, at a given temperature. Which of the other containers represents an ideal gas at the same temperature, but at a higher average pressure? Okay, now here's the thing. When it comes to A, C, and D, they have the same volume as the original container. Okay, they are for original, so they have the same volume, same temperature. Okay, and then so these are not different, right? So only the variables are pressure and the number of particles, because we know that the PV is equal to NKBT. Okay, if the volume is constant and then the temperature is constant, then we can include that in our constant here. So then the pressure should be equal to constant times the N. So I have included volume and the temperature in this constant together with the Kb now. Okay. In other words, pressure is directly proportional to the number of particles. Okay. So that's the situation here. And then that means if you want to have a higher average pressure than the original container, the only way it could do is by having a higher number of particles. In option A, we have lesser number of particles. Therefore, this will have a lower pressure than the original container. In option C, we'll have the same pressure as the original container. But when it comes to option B has a difference now, right? I mean, we have the volume of the option B is double, means twice as the original container. Okay, so if that is the case, for it to have a higher pressure, or let's say the same pressure for the, to begin with, okay, for it to have the same pressure as the original container, then it should have twice the particles, right? So because because the volume is doubled now, to have the same number of collisions and the same number of collisions to have the same pressure, you need to have twice the particles as the original container. That means we need to have 8 particles. All right, now we have 1, 2, 3, 4, 5, 6, 7, 8, 9 particles, meaning we have more particles than what we need to have the same pressure. Therefore, it should have a higher pressure than the original container. Therefore, B should be our answer. Okay, let's try another one. Let's say version A. Okay, so the version A says we have the ideal gas, same situation, but which of the other containers represents an ideal gas at the same pressure and the and average pressure? So they should have the same pressure and the same temperature, same pressure, and the same volume in A, C, and D, right? So in A, so now again, it's about the pressure and the number of particles. Okay, because all the others are constant when it comes to A, C, and D. Now we see that we have lesser number of particles in A compared to the original condition or original container. Therefore, we should have a lower pressure, not the same pressure as original one. And in B, we have the volume doubled. Therefore, for us to have the same pressure, we need to have twice the number of particles as our original container. And then what we see is we have 8 plus 1, 9 particles, more than the double, meaning it should have a higher pressure than the original container. Therefore, this should be at a higher pressure. When it comes to C and D, they have the same number of particles as the original container. Therefore, the pressure should be equal to that of the original container. Therefore, the correct answer must be C and D. For that. And then let's go to version C. And here we go. Okay. So which of the other containers represents an ideal gas at the same temperature but lower average pressure? Now again, remember we're talking about the same temperature, same volume when it comes to A, C, and D. And then if that is the case, the pressure is proportional to the number of particles. In A, we have a lesser number of particles than the original container. Therefore, we should have a lower pressure than the original container. C and D have the same number of particles as the original container. Therefore, they should have the same pressure as the original container. And option B has more particles. It has a higher volume, twice the volume as the original container, but it has more than twice the particles as the original container. Therefore, the pressure here should be higher. Therefore, the correct answer for this should be here. That's the one with the lower average pressure. Okay, so that's how you tackle that problem. Yeah.